Good afternoon. Thank you so much for joining us for what's going to be a not just informative, but I promise you very inspiring hour together. So I'm joined here by David Gruber and Dr. Robert Shelton, and we'll be talking about impact computing, modeling and simulation, and high-performance computing to improve life and understand life, and not just human life, but extraterrestrial and even whale life. So get ready. We're very excited to share with you what we're up to. Thanks.
Thank you.
So, as I mentioned, we want to explore how impact computing, that is computing that intentionally tries to improve life, whether that is human, the life of other species, or indeed entire ecosystems, is evolving, and giving us an opportunity, particularly in the context of this conversation, to actually recenter our perspective and not just think about our individual well-being, but obviously, as is increasingly urgent, to think about non-human health and wellness of our planet, of our ecosystems, and perhaps even eventually of beings we have not yet met, but thanks to the work of my colleagues, may soon. I'll begin by outlining what we're beginning to learn here at AWS about bringing not just humans in the loop, which is good, but bringing life in the loop, much more complicated. We will also then talk about the implications for simulation technology and high-performance computing and how we're beginning to weave into those services and roadmaps what we're learning through engagements like these. And then we will hear from our guests who will inspire you and I'm sure wow you with the beautiful work that they're doing. So, as I mentioned, notions of human in the loop have been very helpful in helping to develop and indeed humanize technology. Watching me, watching my phone, watching me, doing a game is useful, right? It builds empathy. We can understand the human dynamics, the psychological dynamics, the haptic implications of how we interact with technology, and therefore make it more useful. But I think by observing humans interacting with machines, we're really only beginning to scratch the surface of the potential of what we can do to actually use technology and especially advanced compute to really understand and improve life and well-being beyond just our intersection with machines. And that's where we're beginning to think a lot about what the notion of human in the loop or life in the loop might look like. Urgent global and social environmental challenges require that we go beyond human-machine interfaces to consider how we might actually analyze, model, understand, and simulate very complex behaviors. Behaviors that engage human communities, not just individuals, economies, which obviously are controlled by humans but somehow have a logic of their own, animal behavior, and natural ecosystems. These are complex, they're adaptive, and they're living systems. And we need to understand the data architectures, the data analytics, the modeling approaches, and the simulation technologies that are appropriate to the intersection of these living dynamic systems, so that we can begin to understand the ways in which life evolves and hopefully improves in health, in resilience, and diversity, so that we can reclaim really the dignity of all of life and use technology to do so. And that's really the great privilege of working on advanced compute, is that it actually not just allows us to push the boundaries of what we can do through modeling, simulation, AI, ML, and HPC, but through that really expands the imagination. And you're going to have your imaginations blown, I promise, in a few minutes when our colleagues speak to you. But that's really the beautiful promise, I think, of the work that we do together, is that it can expand our imaginations and here actually build empathy and indeed recover the dignity of all living beings. And I'm very proud that here at Amazon, we have made social, environmental impact, responsibility a core commitment of who we are as a company. Those of you who know us know that our leadership principles are not values that we put on a wall and put on marketing materials. We live by these every day. We hire according to them strictly. We make decisions on a literally day-to-day basis. We do hashtag builds trust, hashtag customer obsessed. And we know what that means, right? They're shortcuts for very deep commitments that we have to working in a certain way, showing up in a certain way with ourselves and especially with our customers. And in July of 2021, we added this leadership principle, which expressed the centrality of taking responsibility for the primary, and I love this, the secondary also, effects of everything that we do. And we made a commitment as a company to leave the world better than we found it. And I think what we're doing with our colleagues here is an expression of that. And I'm very proud to lead an organization at AWS called Global Impact Computing that sits inside of our specialist organization, which is another expression of this commitment. Really, it's a kind of engine to drive the ways in which we can take account for the primary and secondary impacts of our work and also leave the world better than we found it. This commitment is to drive social and environmental impact by deploying the company's core assets, our engineers, our solution builders, our business strategists, to understand how customers like the ones you're about to hear from us and hear from, and partners are trying to move the needle on improved life metrics and design back from that ways in which we can deploy existing solutions in ways that are specifically and rigorously relevant to use cases and workloads that are about improving life. And also perhaps build a new set of solutions and services that are what I like to call impact native. Right? We all know what cloud native solutions are. They're very different from on-premises solutions. There's a delta there. And our team is exploring the possibility that, yes, we can deploy the tools that we have more effectively today for social and environmental impact. And there's also an opportunity to ask this basic question: might we, if we design backward from wanting to improve life, actually develop technology that is different? We think that we can, and we're exploring that together. And so we, through Impact Computing and our colleagues in the sustainability teams, are doing this together. And we are excited to bring this not only to impact spaces, but to adjacent spaces where we can think about everything from supply chain resilience and stability and the ways in which efficiencies there can actually travel across sectors. And we're working right now in these 6 areas: climate risk and resilience, health equity analytics, particularly the social determinants of health, conservation, circular economy tools, ESG, environmental, social, and governance indicators, as well as responsible AI. We're also thrilled to host the Amazon Sustainability Data Initiative, which has implications for the work you're going to hear about today in oceans, with marine life, as well as with what we do in and through space. ASDI, as we call it, is a 71 petabyte data store that includes 145 data sets with some of the world's most important sustainability related data. ASDI's mission is to reduce the cost, the time, and the technical barriers to extracting knowledge and insights from very large and diverse data sets. Through ASDI, we also provide cloud grants to democratize access to that data and also build the capacity of data scientists to use that data, which is coming into ASDI and also being generated by the programs that we have through ASDI. We are hoping to build an entirely new cohort with partners like data.org and others that see themselves as impact data scientists. And we want to deploy them across the world for climate change mitigation strategies, conservation strategies, and all manner of social and environmental impact work. And we hope that you'll consider applying for one of these grants and or reaching out to me so that we can design a proof of concept perhaps and explore what we might do together using ASDI and using the advanced compute services and solutions that we help curate. ASDI works with scientific organizations like NOAA, NASA, the UK Met Office, and the government of Queensland and Australia to identify and host and deploy key data sets in the AWS cloud. This includes weather, hydrological data, air quality data, ocean data, and increasingly the extensions of those into health and the ways in which climate impacts health and well-being. These data sets are publicly available to anyone, and as I mentioned, we sponsor this grant program through which we can build capacity. So we're also innovating at the instance level and at the service level. You've heard of the work that we have done through some of our chips. So we're actually innovating in silicon to increase sustainability, reduce carbon footprint. But we're also doing that at the service level. And in my team, I'm particularly excited to be with customers and partners like the ones who are joining me today to push the bounds of what we're doing through our core services. With high-performance computing, we are driving million-plus core runs to try to understand how to do things like democratize drug discovery, create the precursors to quantum chemistry to begin to remediate PFAS, forever chemicals. You may have heard Adam, was it yesterday, in the keynote talk about our work with the Dana-Farber and Harvard Cancer Center, where we did what is probably the largest cloud run ever on any cloud, 5.7 million vCPUs that allowed our colleagues to analyze almost 80 billion molecules, which was an exponential increase in what they've been able to do in a matter of hours and days. It's changing the game in drug discovery. This is changing the game in conservation. So we're very excited that these use cases force us to think about how to provide hyperscale compute capacity through the cloud in ways that are very efficient and cost effective. We're also very excited to be working around computational fluid dynamics and high performance computing. Dr. Shelton will say more about that and its implications of that kind of analytical work for the development of what will be the world's largest telescope. With AI/ML, we're finding that there are really interesting ways to deploy AI/ML at the extreme edge. In the middle of the Pacific, to think about tuna fishery sustainability, or in forests to think about illegal logging and wildfires, and the ways in which we can deploy IoT-driven analytics is providing a very interesting opportunity to innovate within these services. And so what's very exciting about our work together is that we get to drive this innovation through the heart of the company, through our top engineering teams, and through our top business strategists and go-to-market strategists. Impact computing isn't philanthropy, although we do hold to the love of mankind, of humankind. It's an investment by the AWS core services to deploy its most sophisticated resources to create market-relevant solutions that intentionally and demonstrably improve life. And we are committed to mainstreaming social impact in the heart of the business. And I think this is a very important movement that's emerging, not just at AWS, but really across the enterprise generally, is to certainly leverage philanthropy and marketing and ESG and CSR, and in addition, to build an impact stream within the core of the business so that we can actually build disciplined, market-relevant solutions that can actually persist beyond what we've been able to do to date, and we're very excited to be doing that. And in the context of the conversations that we're about to engage in around whale communication, as well as the potential to explore the universe in new ways, we're particularly interested in the power of agent-based modeling, which simulates the actions and interactions of autonomous agents, whether they're individual or collective entities such as organizations or communities or indeed economies. And in the context of the Sustainable Development Goals, it's very important to begin to model how entire economies function in order to understand the behavior of a system and what governs its outcomes. This is critical for understanding economic behavior change in public health strategies, and also green consumption patterns, norm setting in political settings, and radicalization and anti-radicalization strategies among populations, particularly in the context of emergence, right, which in our world is constant and persistent. Just to give you a quick sense of what we're doing around modeling and simulation, we're very excited to be developing some work around computational economics. We're working with Fidelity to apply the AI economist methodologies that have been developed by a team at Harvard and Accenture to apply agent-based modeling to modeling economic policies like universal basic income and equity of access to retirement and mortgage instruments at a macroeconomic level. With a very interesting European startup, Lucid Minds, we're developing approaches to natural resource marketplaces and urban sustainability modeling in ways that bring simulation to carbon economies and carbon credits. With Oxford and Xerox PARC, we're developing a digital twin of national economies to simulate the effects of macroeconomic policy. And with conservation partners, we're actually building digital twins of the Earth at a very high level of resolution to begin to understand green density and its forests and its implications for carbon economies. And with another partner, SimScience, we're building the infrastructure for agent-based modeling approaches to macroeconomic simulation as a service. So by moving away from rigidly human-centered approaches to sustainability and to social impact, we can begin to explore how the dignity of other life forms, and perhaps life forms we haven't yet encountered, can help us to move beyond human-in-the-loop technologies and mindsets to broader and more generous, perhaps, approaches to bringing all of life, indeed all of life, into the loop. And so with that, it's my great pleasure to bring to the stage Dr. Robert Wilson, who is the president of the Giant Magellan Telescope.
Thank you, Nelson. Well, good afternoon, everyone. I appreciate your coming to this session. It's great to look out and see all the faces, and I think you will be intrigued by what I and my colleagues have to say this afternoon. You heard the name. Better get it up on the screen. My background is actually physics, experimental physics, and I, like most of you, maybe all of you, had the opportunity to hear Adam's keynote speech yesterday. Very inspirational, very thought-provoking, very challenging. And I was particularly thrilled when he started off by talking about the vastness of space. He then went on to talk about two great space telescopes. The Hubble, it's been up for quite a while. I was fortunate to be on the Hubble board when we got Congress to fund the servicing mission for. That's why it's still up there. Thank you, Senator Mikulski. And of course, the recently launched James Webb Infrared Telescope. Incredible pictures coming back, inspiring all of us. Well, today I'm going to talk to you about the next great ground-based telescope, the Giant Magellan Telescope. And I think you will be impressed with what you hear. And let me make it clear, I'm not doing this. It's my technical team. It's the people from Amazon Web Services. It's the AI. It's the software programmers. It is everybody that I have the privilege of standing up here and representing. So if you haven't heard about the Giant Magellan Telescope, it is probably the largest public-private partnership in science in history. As I said, we're building the world's most powerful telescope ever. We are going to create a telescope that has 10 times the sensitivity of the Hubble, 4 times the resolution of the Webb. No existing ground-based telescope even comes close to the Giant Magellan Telescope in its power. Physically, it's 3 times the size of the world's current telescopes and up to 200 times as powerful. And of course, like the name would indicate, giant, it is huge. Okay? It is 22 stories tall, nearly the footprint of a football stadium or a soccer stadium, depending on how you look at it. And it can accommodate up to 10 powerful instruments at once, more than any other telescope in its class. Each of these instruments is the size of a school bus. Each of these instruments costs $20 to $40 million, so think giant. Okay? To gather the light, the Giant Magellan Telescope will harness 7 of the world's largest mirrors, as well as some of the world's most sophisticated computing technologies to help understand the fundamentals of our universe. Each of these mirrors is 8.4 meters in diameter, and there are 7 of them, giving us an effective diameter of 25 plus meters. The Giant Magellan Telescope will allow us to study the properties of planets around other stars, searching for life elsewhere in the universe, millions, billions of light years away. Ultimately, the Giant Magellan Telescope will be humanity's very best chance, maybe its only chance, to answer the age-old question, are we alone in the universe? While also helping us to understand our own home a little better. There's only one Earth, at least that we know of. So I think it's fair to say that humans, as long as we've been on Earth, we've been looking up in the sky and wondering, what does it all mean? What else is there out there? Are we alone? From the very beginning, we've been obsessed with the sun and the moon. Why does the sun come up every morning? Why does the moon rise at night? And the stars? Well, we've been captivated by the stars. We named them. We idolized them. We wrote songs about them. I remember those as a child. And of course, we turned them into heroic characters. Eventually, people staring at the night sky recognized patterns. Patterns among the stars, and we call those constellations. They saw that the patterns changed with the season and could be used to navigate by land or by sea. And we also noticed that some of those objects, we thought them stars, moved around a lot. These stars seemed to wander in and about and around the constellations. And of course, we eventually learned that the wandering stars are actually planets. Mercury, Venus, Mars, Jupiter, Saturn, planets within our own solar system, and their wandering is really the orbits around the sun, which is where the word planet comes from in Greek. Planet means wanderer. So this new planetary revelation invited a period of enlightenment. It rewrote our story. It strengthened humanity's desire to know if we were alone in the universe. It was an exciting time to know that Earth, our home, was not a lonely planet as people once believed. So people began to wonder, if our sun has multiple planets orbiting around it, could other stars in the universe have them as well? And the amazing thing to me, remember I said I was a physicist, not an astronomer, so this really startled me. It was just 30 years ago the existence of planets outside of our solar system was merely a theory. And then 30 years ago, the whole idea changed. Until then, people thought our solar system was unique in the entire universe. Maybe that's a bit of chutzpah that we have as humankind. And we thought even if there were other planets out there, we'd never be able to see them. They'd be too far away. They'd be too faint, hard to identify. The technology just wouldn't exist. Well, surprise. Brilliant scientists discovered the first planet outside of our solar system in 1992. And here's what it looked like. Wow. Okay? Now fast forward to today, and what we have identified are billions of planets and confirmed thousands of individual planets orbiting a wide variety of stars throughout the Milky Way galaxy, our home. Yet each is different. Each has very unique and we think interesting planetary properties. Okay. Some, of course, are gas giants. Some are made of ice. Some are made of rock. Some have almost circular orbits, and of course, the others are elliptical orbits. The universe is simply filled with extraordinary planets to be explored. And while all of these different planets have their unique characteristics, the one thing they all have in common, is that these planets were discovered with a telescope. That's what telescopes do. Telescopes collect light from celestial objects in the sky and allow us to see extremely far into the universe, way beyond the natural ability of our two eyes. In the case of the Giant Magellan Telescope, it's up to 15 million times more sensitive than the human eye. Think of telescopes as real-life time travel machines. We know light travels fast, but not infinitely fast. And so we can look back in time by looking at objects that are far away and very faint if we have the observing power of the Giant Magellan Telescope. It takes millions, sometimes billions of light years distance for those signals to reach us here on Earth. Now, we've been building these time machines to capture light for over 400 years. Ever since Galileo, the quest has been to build bigger and better, not just bigger, but better telescopes, so we can collect more light and see more distant objects hiding in the cosmos. Bigger telescopes produce sharper images, and that's very good for science. We have been building telescopes, as I said, for 400 years, and now, today, the Giant Magellan Telescope is our best chance to capture the universe's ever fainter lights from ever more distant objects. Each of the Giant Magellan Telescope's powerful scientific instruments has a unique ability to explore the unknown. For example, analyzing a distant planet's atmosphere in search of life, looking back to when the universe was first formed. Together, the light-collecting power of the primary mirror segments and the instruments will answer the ultimate question of whether we are alone in the universe. Now, this may all sound very grand, and it should. It's certainly what attracted me to the Giant Magellan Telescope. And the answers we find could transform the human experience. But it all really starts with understanding whether a planet is habitable. And by habitable, I mean for carbon-based life as we know it here on Earth. Because right now, Earth is the only known planet that can host life. We know from the planets we've already detected in the Milky Way galaxy that this galaxy hosts as many as 50 billion planets that could possibly host the ingredients for life. But similar to the difficulties we had finding a planet outside of our solar system, remember that was just 30 years ago, now we face a new technological hurdle. We simply do not yet have the ability to characterize and study a planet's atmosphere to detect the elusive signatures of life. The signals so far are too faint. The signal to noise is not strong enough from our current suite of ground-based telescopes or our space telescopes. Now, those of us in the telescope building world know that every step we take to improve the resolving power of a telescope's design is a hard-won battle. Leaps in resolution are not made very often, roughly every 30 years or so. That's why we are thrilled to partner with Amazon Web Services. The expertise that Amazon Web Services brings to us in high-performance computing and big data services is helping to revolutionize telescope design. For starters, the Giant Magellan Telescope's massive mirrors, these are 18 tons of mirror, need to operate in an optimal environment. The telescope is being built in the Chilean desert, the Atacama Desert. It's one of the driest and harshest places on Earth. The extreme temperatures, the changes in those temperatures, and the wind pressure from the desert cannot interfere with the revolutionary optical performance of these mirrors. Here's an example. Amazon Web Services is helping us optimize this giant 22-story smart home that protects the mirrors. 22-story building, and it rotates. You want to have 360-degree view of the cosmos. AWS is driving our computational fluid dynamics simulations so we can predict the image quality that the telescope will deliver under various climate conditions. Thanks to the high-performance computing ability, we're able to also simulate any changes to the telescope design and troubleshoot problems before the telescope is built, saving us enormous amount of time and money. Did I mention this is a $2.5 billion public public-private partnership. So time and money, hand in glove, very important. Computer modeling on this scale has never been done before in telescope design. These new techniques, we believe, will become standard for the development of future large telescopes, thus saving the whole industry significant time and funds. We think this reduction in cost and increase in design effectiveness while helping the existing telescopes improve their operational efficiency is a tremendous contribution from Amazon Web Services. From day one, the Giant Magellan Telescope has worked with Amazon Web Services to run high-fidelity computer modeling and optomechanical structure of the telescope, performing the virtual assembly, integration, and testing of the telescope components before the final assembly in Chile. The integration, the integrated model of the telescope, not only improves the design of the observatory, but it also provides significant benefits for software development and control algorithms long before the actual hardware is even available to test. Using the observatory equivalent of a flight simulator, we can improve software quality and user interfaces to optimize control algorithms and analyze observing efficiencies. In the near future, opportunities also exist for additional leaps in our advancement by implementing Amazon AI and machine learning technologies to complex data handling processes for the Giant Magellan Telescope. So, the fundamental message here is, with the support of Amazon Web Services, the Giant Magellan Telescope is well positioned to make a quantum leap in spatial resolution and light collecting power, and this will make what was once considered science fiction into a common reality. As president of the Giant Magellan Telescope, I, along with my colleagues, are on a mission to empower human knowledge. I want to see farther into deep space with more detail than ever before. We are all focused on assembling the resources and international relations required to build the world's most advanced telescope. And I know that once we finally solve this and the Giant Magellan Telescope is in operation, the question, are we alone in the universe, will be answered by this next generation in technology. We absolutely rely upon, depend upon companies like Amazon Web Services to provide the computing power necessary to design, to test, build, and then, once built, improve these technologies. One of the beauties of ground-based observing is it doesn't cost $1 billion to run a servicing mission. This telescope will last for 50 years and will continue to improve because of the brilliance of all of you with Amazon Web Services, the brilliance of our instrumentation people. It will get better and better. So thank you. We need you, and I believe we need the Giant Magellan Telescope as well. I now ask Dave Gruber to come and talk about CETI, his project. Thank you all.
Thank you. Wow, totally blown away. Thank you. Thank you, Robert. And it is a pleasure to be here and to follow humbly in the footsteps of such a project like this that's asking existential questions of like, are we alone in the universe? Something that really makes us human. So I'm here today to describe and tell you a little bit about and share about Project CETI, the Cetacean Translation Initiative, which is aiming to be the largest interspecies communication effort in history. And so if we do find life out there, that we might use some of these technologies to talk to the aliens that we'll see with this Magellan telescope. And I think thinking about space and thinking about perspective, this image was only taken, 53 years ago of seeing the pale blue dot from the moon, and just how that changed our look of this planet. So as we look outward into this void, there is that thing of this tiny, delicate planet here and what it holds for us and how fragile and how much we must protect it and study it. And many of the astronauts that go out and are able to have the honor of looking back from space at the Earth are profoundly impacted by the overview effect of and wanting to actually protect the life on Earth and study its mysteries. So where we're focusing the lens of our telescope is on sperm whales, or I like to call them by their scientific name is Pfister macrocephalus, which means the large head. I mean, they have possibly the largest brain in the universe. They at least have the largest brain on our planet, an 18-pound brain that is 1/3 highly encephalized, and live in these complex societies, matriarchal, and use a kind of almost like a cryptic Morse code-like communication that occurs in both sexes, whereas sometimes you're probably more familiar with whale song, which is sometimes only among one sex. So I'll just give you a little idea into a portal into the sound communication of sperm whales. So thinking about this, much of what we know, we didn't even know that these animals made sounds until the 1950s, that sperm whales made sounds. But much of what we know about this Leviathan, this is essentially Moby Dick, which has been portrayed as a villain and a beast, which is actually the few people that have had the honor to get to really interact with these know them as gentle giants. And how they make the sound is they have these phonic lips which they move, which then transmits through sometimes more than 500 gallons of spermaceti oil, which bounces off the back of the head in what's known as the bent horn hypothesis. And then it goes through this series of ossified waxes. And it could actually direct that into a tiny thing, like a little squid, or it could project the sound outward. So they have very good control of their sound. And they're using that. Essentially, they hold their breath for over an hour, diving into the depths, searching for squid, or much of this is not very known. There's only a few minutes of footage of what sperm whales are doing at the depth. Much of what we know is just from the surface and listening to them while they're down there. But we do know that they're making echolocation clicks, which is the loudest biosonar also in the universe. But they're also making these short clicks that are known as codas, and just beginning to understand a little bit about the information that is carried within the codas. But as we dive into this, we actually see that it can hold much more information than we thought. So the capacity for information transfer within these codas is quite vast. And I think about this time that we're at now and just the amount of power that we're projecting at ourselves, because it's commercial, because we could sell stuff to each other. So we, of course, know so much about human language with these large language models and just the power in which we're looking at ourselves. And now we're able to translate human languages, not even by using any kind of Rosetta Stone or dictionary, but just by looking at the languages in multidimensional space. And that we're actually seeing that, we're not as distant as we once thought. Languages that we thought would be so complex that we're all Homo sapiens, we all are humans. And when I started thinking about projecting this lens to whales, I was looking at, how was this studied before and what do we really understand about the sonic system? And this led me to the work of Shane Garrow, who had ran the Dominica sperm whale project, and over 15 years collected a database in the size of in the tens of thousands, carefully annotated, collected, that was telling us really important things about whales, showing that there's distinct dialects among groups. And he was doing it with these kind of off-the-shelf tags that were mainly made for dolphins and smaller marine mammals that were available to kind of piece together a little bit into the inner portal to their world. And I was a fellow at the Radcliffe Institute for Advanced Studies at Harvard in 17 and 18, And while I was there, I got invited into these machine learning seminars that were being held with Shafi Goldwasser and Michael Bronstein. Shafi is a real giant in the field of cryptography, has a Turing Award, and invented the gold standard of the internet encryption, so how we could do our banking online. And Michael, who's the AI professor, the DeepMind professor of AI at Oxford, has been one of the early pioneers into geometric deep learning and graph machine learning. And some of this technology is probably more known, called Fabula AI, which is used to detect fake news at Twitter, came together, and we really began to kind of say, like, what would happen if we took this database and we actually went larger? Is the technology available? So we organized a seminar at Harvard as well, where we just brought about 20 people together from different disciplines, from robotics, from machine learning, from whale scientists, and we all sat there, and there was this moment in the meeting where we just realized that just as the window has opened with the technology available to look out into the universe or for translating among human languages, it's now possible to actually follow these whales into the depths and get the information out to train the computer to be a baby whale, so to try to learn the language from the bottom up. And I remember sitting there, and we held a meeting, and then Daniela Roos, who's the director of MIT CSAIL, kind of set out, she's like, you know what? This technology would be the same technology that we would use to talk to aliens. And I remember kind of like chuckling and looking around the room, and everyone was dead serious. Like, so we put together a proposal in 2020 and were awarded the TED Audacious Prize, which is housed by, which again is an organization housed by HEAD, which gave us the seed funding to move this project forward, to decode the communication of whales with advanced machine learning and state-of-the-art robotics. And so we've now grown to over 30 scientists that are coming together from, again, all different fields. We're coming from linguistics, from machine learning, from cryptography to biology, and different organizations. You know, AWS, the open data, has been incredibly helpful as the data lab. We've got National Geographic as a partner, Google's on board, Harvard, MIT, CUNY, Berkeley, Texas A&M, Oxford, and one of the really special partners is Dominica. As we partnership to build, basically take the data set from the Dominica sperm whale project in the tens of thousands and turn this into the billions and maybe trillions. And working with this family of whales there, you know, this is an island where these whales still exist and the ecosystem is still in a really pristine environment. And it was really important for us in working in the Global South to see this as a true partnership. And we just held one of our first annual meetings there in August, and over 30 members of cabinet came to the meeting, and as we kind of move forward in this joint effort together. So you want to hear, like, how are we going to do this? You know, how are we going to understand whale speak? So a little bit about the tech. You know, there's many different forms of tech. So we need whale-attached robots, and working again with Rob Wood at the Harvard Microrobotics Lab, who's well known for robotic bees. And for really small things, but part of our philosophy in this project is not to draw a single ounce of blood, to try to be as minimally invasive as we can. So we can't suture anything or you know, even get any blood samples from this. So everything is non-invasive, which is forcing us to be even more creative as we go about this endeavor. There'll be aerial aquatic drones that'll be taking pictures from the sky, as well as maybe collecting some fecal samples, which we could look for things like microbiome and hormone analysis to get the physiological state. Free swimming robots, tethered arrays, which are where we're really getting our core data from, as well as surface drones. So this is the secret sauce, you know, the diagram, the 5-step diagrams to how we would understand whale speak. So essentially we start out with this raw audio, and we need context, you know, especially from the linguistic team. Without context, it's really difficult to understand another communication system. That's why working from previous data sets where you just hear the sounds but you don't have any context, you might be able to find some sort of deep structure, but you really can't know what was happening there. That'll then fly into the machine learning engine where it's going to get structured, where it gets fed to the linguistics team, where we'll look for things like recursion, syntax, structure. We have a real theory division among CETI, which is kind of generating a lot of the ideas. Something like fault tolerance, like you ever been to a crowded bar and you'll notice that as the music gets louder and louder, you start, your communication gets more and more terse, like, I'll be right there. And you might even say something 3 times just to make sure that you get your message across. So giving us theories of things to look at, as well as even like showing time displacement. Like, is a whale talking about an event that happened yesterday? Like that alone would be a major finding. Once we get these language fragments, we could then synthesize these codas and very carefully, and we're actually putting together an ethical panel thinking about this, because as we do get up to the state of understanding the communication system and replicating it, of how and when should we communicate back. And starting out, it's really just to validate our findings, that we think that we understand it to a level that we can go back, but it really brings up a deeper thing for humanity if we could understand non-human communication. Just a little bit more about our ecosystem and how it's working. And here is the robotic tag that is coming out of Rob Wood's lab. There's so much going into this. Even the suction cups, the whale's skin, because they're mammals just like us who came out of the ocean onto land, but then went back in. So they're a really weird example of evolution, and their noses rolled over and became their blowhole. And but their skin, is not like a fish, so they've developed this way to kind of keep sloughing their skin. So getting something to attach onto them is actually quite difficult. And there's an entire PhD just on adhesion, on thinking of ways that we can get these suction cups to stick on, and having another mechanism of a chemical reaction might cause more of a suction as after 12, 15 hours to keep them on longer. And here I'm going to show you, this is one of the early videos of showing from an aerial drone as well as from the tag of 2 whales communicating, just to give you a little feel here. Yeah, this is one of the first times I've showed this video in public. Anthony Tarabella from MIT is working on looking at body language from among this to see is there anything, as I'm talking, if I want to get aggressive, I might, hunch my shoulders in or something like that, which could give more information as we try to decipher their communication system, as well as algorithms that could really remove the water so we could analyze this with big data. But how we're really generating our big data in this project is the core whale listening stations, 3 of these that are going in Dominica that are going to cover 20 square kilometers. And they're being designed by Roy Diamant of the University of Haifa's Underwater Acoustic Navigation Lab. So there's a series of microphones that are each one's residing on what's known as a whale recording unit, which allows you to triangulate and beamform. And so therefore, we're hoping when the whales are within our array, we'll have a really good view of what they're saying, combining this with the high resolution data that we're getting off the tags. What I think is interesting among people from AWS here is like thinking about the pipeline, because we're so used to working with human data. So the idea here is like, how do we get this communication data out from a mile deep up and put it into the cloud? So we were able to use, showing you the tech that we're using, but then we beam it from the buoys onto to an antenna on the shore, and then how do we get it from there onto the cloud? So we're looking at satellite solutions, as well as using things like the AWS Snowball or sneaker travel to be able to bring it somewhere where we could actually get that data up there. As we move forward, we've now acquired three boats that are used in this effort, and sailboats are really important because they don't make any noise, and they're also quite fun to spend several days at a time with the whales. But we're thinking about, how do we go from rather small data, which is quite common in the animal communication fields, into the big data that we have in human. And for natural language process, we're seeing like model size and computation are really increasing exponentially. And how we're going to look at this from our big data set. So we're going to be looking at a 20-kilometer area squared off the coast of Dominica, where there's about 50 to 400 whales that are, depending on season, vocalizing quite continuously. And if we then separate out about 3/4 of their communication is from echolocation or finding food, we're still not sure if they're harboring information in that, which is still quite possible. And about 1/4 of that are these coda socializing at the surface. So we could kind of estimate if there's about 1.25 clicks per second, and we could get between 400 million to 4 billion clicks a year in a good day or a good year if the whales are always kind of communicating and within our 20-kilometer square. If we got half our funding for this project, so we actually wanted to expand this area to 40 kilometers. But it's now just the waiting game to get to that big data size. But even so, looking at the Dominica sperm whale project that had less than 100,000 tokens, so that's a dot that you can't even see on this graph here, we're hoping to get up into the 0.4 to 4 billion, which is still quite small compared to something like GPT-3. So a little bit more about how this is going to happen, the architecture. So I mentioned we're coming data from many different sources, from drones, from audio, to environmental data that's going into the S3 bucket, where it will then be processed with EMR. And then we're thankful to the AWS Open Data Sponsorship Program. It'll go into another S3 curated bucket. And then from there, the different machine learning teams will be working with Amazon SageMaker, looking at click detection, and things of that sort. We also really want the whole world to come on this project, so that's what the great thing with the Open Data Program. So we could think of Kaggle competitions and ways that we can really get everyone that computes to play a role in helping us crack this interspecies communication. From there, if it looks like it's good, it would actually go into the Amazon Open Search Service, but if we're not getting a high confidence, it would go into a human in the loop where it would get annotated. So that's a little bit more on this, and we have Vamshi here from the AWS team that is helping with the AWS Data Lab, which will be running next week with the team to get this up. So, I mean, these animals could be the most intelligent beings in the universe. I mean, they have spindle cells in a neocortex, structures that in humans control things like language, love, intuition, and we're now just beginning to understand. And the algorithms in the machine learning that we use to get a better portal into this could really be applied to any animal once we get this worked out. We could use this for dolphins, for killer whales, for elephants, for bats, for aliens. And it was in the 1960s that one of our chief advisors, Roger Payne, discovered that whales sing. Just a simple thing, that there's song. And this discovery, that whales sing, was one of the most powerful things in the environmental movement, started the Save the Whales movement, led to the Endangered Species Act, and likely saved many whale species from extinction, just by knowing they sing. You know, and in essence, this is really a deep listening project. And I think every generation always feels like, oh, we're at the generation that's the most important generation ever, we're really at the crossroads. And I mean, I guess we're all biased, but I think it feels more than ever that that's true, that we really are at a crossroads. And how do we want the future to look? And we know that technology is going to be in our lives, and it plays a role. And do we want to build an equitable, beautiful future where we're using technology to like understand and communicate with life and find life in other galaxies that are billions of light years away? Or do we want to use it for kind of less pretty ways? But now is the time to deeply listen, and I'm really excited for what the future could hold. Thank you.